So let's talk about quantum computing for materials discovery. We have about 20 minutes. The topic is huge, so we just go in the medias res. And the medias res is actually this particular slide. We want to tell you what's the whole fuss about. It's about this triangle. So this is the holy grail of material discovery. The idea is to know what do we get at the end as a final product properties before we put anything into reactor. So I'm a chemical engineer, so that's what I worked, let's say, more than 10, 15 years on this particular triangle. And it's complicated because it's not that simple. So just to give you a feeling about this thing, I selected one very interesting chemistry. It's a bread chemistry. So you see, we have only a few ingredients. It's basically water, yeast, salt, sometimes there is no even yeast at all, and flour. And depend how you mix it, how long you mix it, temperature, and all these kind of things, you will get certain properties of the dough. It's a material property. Here we selected just once. So these protein chains in the flour, when we add water, they will form a network. A network will capture air, depends how we mix it and temperature and all these kind of things, and we bake it. At the end, we either get a Italian focaccia, very soft with a lot of bubbles, yummy, or we get sour bread. It's also yummy, but there's not a lot of bubbles because it's completely different idea, right? So if I'm a baker, similar if I'm a chemist, I want to know my recipe for focaccia before I put anything in the reactor. So this is valid for any material on Earth, being it battery, being it cosmetics, chairs, car parts, everything. And companies who understand this triangle will actually succeed in the future. Why is this important? Because when we experiment, there are millions of options. You have seen Microsoft with, I don't know, 3.6 billion combinations. But not all of them will give us money and good product at the end. Only a small portion of it is actually viable solution. The rest of the dot, you're just spending money, time, resources all over with no result. And even if you find your orange area, you have another problem. 70% of researchers cannot repeat the results of other researchers. We say, well, whatever. That is okay, but 50% of researchers cannot repeat their own experiments. And if you're a chemical company, as I was in, as Marcel is running, it's a little bit of a problem, right? So it costs you a little bit of more money. And combine this with a little bit of regulatory, as we have heard this morning a lot about regulatory, it's no wonder that a new drug, requires 15 years and almost $3 billion to be developed, and any material, maybe 100 plus millions and up to 5 years to be developed. So where is our hope for this case? Because in Europe, especially, we need to be faster, right? We need to be bolder as well. So the hope is in this constellation. So and this is the first hype. Anybody telling you that quantum computing is the best thing since the sliced bread? Well, not really. It's the best thing since the sliced bread if combined with high-performance computing, which we are using in chemicals and material discovery since forever. If combined with AI and recently also with Gen AI, this is where we get to accelerated materials discovery. And just a few words on quantum computing. It's not just faster computing. It's a completely new way of thinking. And I have no time to go into this reaction, but it's production of ammonia. This particular reaction is, if any is chemist around here, is a Haber-Bosch process. It's a Nobel Prize process that was feeding the world the last 110 plus years. But if you look at this reaction closely, you will see a lot of harsh conditions, a lot of CO2 leaving the system, exactly where this thing is. And this particular reaction alone contributes about 2% of all CO2 across the world every single year. And there are some other creatures who are not human, but much smarter than we are. Those are bacteria, who produce the same reaction at the room temperature, atmospheric pressure, and in closed energy loop, ATP, but doesn't matter. And all we know right now, and we can simulate with certainty, is this little cluster here in an enzyme called nitrogenase. And our hope with the quantum that with less assumptions, simplifications, and everything what we are doing right now, that we will be able to discover this process in more details. It's not over yet. It's not everything clear yet, because even though there's a lot of discussion about qubits, I think we still have something that is called qubits Game of Thrones. IBM is leading, superconducting qubits are doing great, but there are also some other modalities that might be interesting when we talk about, for example, modeling and simulation of quantum mechanical systems in nature, such as molecules, with quantum mechanical systems, such as neutron atoms or trapped ions. So just be aware. Keep eye open. So that might be something there that is worthwhile exploring. In quantum ecosystem is growing like crazy. There are a lot of quantum companies coming in, like mushrooms. So you can decide on full quantum stack providers such as IBM, my ex-colleagues that we collaborate still. But you can also choose and pick and choose and hopefully plug and play among other providers. Market is very dynamic. Potential economic value, so value that we generate with quantum, is about 2 trillion. McKinsey said so. That means value that we get from new medicines, from new materials, from new way how we manage energy systems and so on. Today, 2 billion are invested in quantum technology, in quantum computing by 2024, and almost doubling the public investment from 15 to 34, it's more than double. There's a lot of dynamics in the market, a lot of M&As since 2021 when Honeywell took over, Cambridge guys. We have just a few weeks, StainWorks acquired Quantagonia. This is here in our environment. There's a lot of insolvencies. Zapata, who used to be the first quantum native company, actually does not exist anymore, even though BSF was collaborating with them. That was a public announcement there. So there's a lot of dynamics in there. And about this dynamics, who will speak better than somebody who is in the middle of it? Marcel.
Thank you, Renata. Not everything is bad. Some news may not look that good, but looking from a, let's say, European quantum native player at Quantistry, there are actually quite a lot of positive things here. If we think about Europe overall, we have a great, strong industrial basis, which gives us opportunities overall for unlocking, on the one side, massive use cases, but also participating in a greater quantum economy. What we've seen, for example, a few days ago, the IQM funding round, which is actually really great. We've also another great advantage here in Europe. Speaking from a startup perspective, there's a lot of great talent. We have great universities, great research networks from which we can source talents, but of course we also need to keep them. And it's better nowadays. There's a lot of early stage funding, which is actually great to get started, to build a company, develop the technology, unlock first use cases. Later stage, of course, the game is somewhere else, most of the time in the US. The only real drawback I see in industry here or in the European economy is a bit the, let's say, slower innovation climate. I think we're not bold enough. We are not bold enough often, even on a startup space, but more importantly on industrial space and in the investor sphere. We need to be more bold and get things done and try it out and accepting to fail on the way. At the end, we will succeed. What does this then actually translate to in industry? I mean, as Renata has shown, you can think about baking bread or think about the production of ammonia. But we've brought today actually a few more really industry relevant and impactful use cases which already affect our day-to-day life. For example, have a look at the first one, where we worked at Quantistry with an automotive company from Germany, where we worked on novel battery materials. And quantum computing is actually one of the key technology to develop purely virtual these materials. They allow us to make more accurate and more precise predictions of properties and performance basically of the outcoming material. And with that also reduce the lab work technically. So in an ideal world, looking into far future, you may be able to do this more or less completely virtually. Another really impactful use case is the one on the following slide. I mean, as you're aware, one of the problems is carbon dioxide in the atmosphere. So we need to have some materials on how to filter basically carbon dioxide of the atmosphere, store it, and then make use of that in other basically industry applications. One of these materials are metal organic frameworks, what you see on the top right, which is quite a complex material overall. And the tricky part here is there are 10 to the power of 60 possibilities or different materials, which is quite tricky to screen even purely digitally, and it's just computationally not feasible. What's super important about these materials, they need to be designed on the one side to take as much CO2 as possible, but also be able to release CO2 as easy as possible, just from an energetic point of view. A great consortium around Fraunhofer, Spinos, and more actually worked on this topic, and they've developed a hybrid quantum classical approach to better understand these interactions between carbon dioxide and this metal organic framework to optimize the material and then ideally at some point get these materials also into industry. But that's not all of it. There is actually way more, and Renata will tell us more.
Sure. Yeah, so this is a company called Sandbox AQ I collaborate with from the US. They are a Google spin-off, $5 billion currently valuation. They deal with material science discovery using quantum and AI. And now came to them about discovery of new catalysts. So catalysts are very important in chemical, in industrial environment. And basically what they have shown that using quantum, in this case they call it massive parallel quantum simulations, they were able to get to the new structure of a catalyst 10 times faster. There is a paper on this, so if you want more details, definitely you can have a look. So the whole point is people are saying, oh, we're going to wait until 2030 until we get the perfect quantum computer fault tolerant and so on. You don't need to. You can play even right now, and those who understand that playing right now, it's very important, they are doing these kind of things. And it's not only about, let's say, material discovery, it's also important, in this case it was Kipu Quantum, just a couple of kilometers away from here, using quantum machine learning for faster image classification. And you think, like, why this healthcare has to do anything with material discovery? It does, because a lot of times we take some images to characterize materials. And if you have atomic force microscopy or some other microscopies, this is very important because you can build your machine learning system, machine learning model much faster. This is what Kipu and University of Valencia have shown. It is not only about materials, it's also about reactions. And this example is awesome. In Germany, we don't talk a lot about these things, but nuclear fusion is one of the future energy sources that we believe as humans might save us, might run all our data AI centers in the future. And India and China are experimenting with this, and this particular paper is actually from a university in India that they use quantum computing to simulate plasma states and some other complicated multi-dimensional calculations of nuclear fusion. They have shown that the computations done on quantum are 75% faster than traditionally. This is done together with IBM. And the last case is not on Earth. So this January, US Department of Energy announced that they want to be, let's say, very forward in space economy. And they believe that quantum technologies, so computing, sensing, and communications will be essential for this goal of dominance in space. So while we are sitting here and thinking about materials on Earth, we might as well think about the future and materials that we will need to travel, to exploit, to live in space. Now, success factors. I will give the first success factor back to Marcel because he's dealing with that on a daily basis.
So, as you see, quantum computing has a massive potential. but you need to collect a few success factors to make this actually happen. One of the most painful ones, as most people also know from the AI field, is data. Despite quantum computing, you need to have data to make use of that, extract the knowledge. And quantum computing is an insane possibility to make this happen. But you need to have high quality data and also ideally a high volume of data. This is still, with quantum computing, an underlying challenge which you need to bring to the table as a success factor to make this happen at the end of the day. But it's not the only one. There are actually quite a few more.
Yes.
So
we have, of course, hardware challenges, and Heike and colleagues from IBM were talking about it just a couple of minutes ago. We will solve them. We have data challenges. We will also solve them. But there is another important challenge and success factor. It's quantum literate workforce. If you remember ChatGPT moment 2022, a lot of companies struggled, and after this moment, they took their data scientists, and suddenly these data scientists became overnight large language model experts. Well, so fast is not going to happen when quantum computing is getting this inflection point in the future. So therefore, companies have to be very careful about quantum literate workforce access to this via universities, via ecosystem, or hiring their own. And I'm talking here not only about quantum engineers, scientists, people who can really, let's say, program quantum computers. I'm also talking about business leaders who are quantum literate and understand what does it mean for my business. How can I use quantum to get a new novel blockbuster drug 3 times faster and earn lots of money with it? And that's valid for all materials. McKinsey is predicting that only 1/3 of all job postings in the future by 2030 in quantum domain will be filled. So therefore, there will be shortage of quantum literate workforce. So if you are in the field and you're thinking about quantum, that this might be for you the most relevant challenge that you need to resolve. Finally, organizational readiness. I've been in companies where it's a huge German nameplate, let's put it that way, and they only have one person who is a quantum enthusiast. It's a very hard, harsh reality, but also there are other companies that I've been where they have figured out their strategy, their technology, their use cases. They have whole departments that are operating as a quantum computing department, and they're just waiting for the quantum advantage to really go into details with their discoveries. So finally, if anybody is asking after all this, when is a good time to start with quantum, I would say, or we would say, right now, or even better, you have already started in material discovery. And if not, pay attention what kind of technologies are shaping up in there. Pay attention where you get your quantum literate workforce now and in the future. And definitely think about your use cases. What are the most let's say, most challenging cases that quantum can help you in your materials discovery. So that's all. We are happy to connect with you and happy to take questions. Thank you.
Thank you.